Welcome to our last video in this chapter where we will be discussing nuclear decay calculations of radionuclides. I'd like to start this portion by talking about the specific isotopes that are used for various purposes. We mentioned that a lot of radionuclides are used in medicine. So this first slide, again, you don't need to memorize or know these, but I always think it's interesting to show which specific isotope. And so that is the nuclide listed in the left column, the type of emission it will undergo, the half-life, and the specific body part that it is used for. So again, specific nuclides are used to target or image for specific body parts. The one that you might be the most familiar with would be iodine 131. If you paid attention to news stories after the Japan Fukushima nuclear power plant tragedies after the tsunami, you probably heard about residents both locally and across the waters being issued iodine 131 that is used for thyroid purposes. So both to image, diagnose, and treat thyroid issues. And then again, just various nuclides and the body parts that they are used for targeting. I also think it's interesting to show students the exposure sources that we often have. So there are a lot of natural nuclear exposure sources that we have. So it is all around us. It's not just from nuclear power plants or just from radioactive sources. Because most isotopes will have a radioactive isotope, it is literally all around us. And so this is listing the source and then the dose. So a note on the dose, the unit that's used here is a millirem. So milli, of course, our metric prefix means a fairly small amount. Rem stands for Rontgen equivalent man, and that's just a unit that's used. So Rontgen is a unit that's used to measure how much radiation there is. If you've ever heard about Geiger counters, they're measuring in Rontgens. And so this is measuring milli Rontgen equivalent man. Natural cosmic radiation, how much we get typically per year. Of course, that's an average. We have radionuclides in our body. Anytime you're getting a dental x-ray, depending on whether they're doing just the bite wing or whether they do the whole panorama, depends or determines how much exposure you get. If you get heart scans, building materials, again, the isotopes that are naturally found as one of the isotopes in material. Luminous watches. Interesting side note for you here. There is a very fascinating and easy to read book called The Radium Girls that talks about when in, I believe it was World War I. Sorry, history is not my forte. World War I, women were hired to paint radium onto watches and dials for pilots for use in the war. And the direct exposure those girls had to the radium by ingesting it caused just tremendous damage and weird, bizarre, and very aggressive types of cancer. So if you're interested, Radium Girls, pretty disturbing, but a very interesting story about the effects of radium as a cancer-causing agent. Tobacco, a little soapbox for you here. If you're a smoker, don't. There's quite a bit of radiation associated with those. So the symptoms of exposure, those are the sources of it. This one lists, based on how much you're exposed to, what symptoms and effects you would expect to see. But notice the difference in units. So the key thing here, remember the previous slide was talking about millirems. This one is talking about rems, so 1,000 units of those. If you get less than 5, so less than 5,000 millirems, there's no observable effect. So obviously as the numbers go up, the damage becomes more and more fatal and severe. And so depending on the level of exposure, it takes up to 2,000 rem to be immediately fatal. All right, into our calculation. So I will start this video or this portion with a review of the reactions that we perform in here. Sorry, not the reactions, the equations. So radioactive nuclide decay all happens via first order kinetics. That hopefully sounds familiar. It's what we discussed when we talked about integrated rate laws in chapter 12 with kinetics. Remember, we talked about first order and second order. And so what we're going to be specifically talking about are just the first order equations. All radioisotopes decay by first order. What's very common, of course, with nuclear particles is that we often know the half-life of an isotope. So we're frequently given half-lives, and then from there we can calculate rate constants. I'm actually going to jump slides here. Sorry, just to remind you what half-life means. So remember, half-life is measuring the length of time that it takes for half of a substance to decay. So if I start with 100% of an isotope, let's say 10 grams, as they show in this graph, the length of time that it takes for that to decay down to 50 grams or 50% is one half-life. That same length of time will take our substance down to 25%. Again, cutting in half every single time. So 100 to 50 is one half-life. 50 to 25 is another half-life. 50 to 12.5 is another, et cetera, et cetera. We keep cutting in half. And so that length of time, our x-axis, is exactly equivalent for every half-life. So then going back to our equations, again, since they're all obeying first order kinetics, remember we use the function natural log as our function to give a straight line so that we can calculate one of two things. We typically will either want to know how much of an isotope is going to be left after a given amount of time, or how long it's going to take for an isotope to decay down to a certain percentage. This calculation, solving for time, is actually used when scientists are having to figure out how long do they have to store radioisotopes in order for it to become a safe level. Generally, they consider about 2% remaining as a safe level. So again, back to our equation, we have the natural log. Notice if you check your equation sheet, the only difference in here, if you remember in chapter 12, we used concentration of reactant A. In nuclear chemistry, we don't measure anything in concentrations. We're not making solutions, and so we don't use concentration units. So the only difference is in 12, we used concentration. In chapter 21, we take out the concentration notation. We also change the A to an N, and that N is representing nuclide. So same definition, same everything, we just changed the notation. So again, that sub-zero tells us how much we have at the beginning of whenever we started measuring. If we're working with percentages, which is very common in nuclear, remember that it's implied that our initial would be 100. The N sub T is the final amount. It's how much is remaining after a given amount of time. And this can be measured in mass, and that can be grams, milligrams, picograms. When we're talking about nuclear substances, we often measure in small amounts. So any metric prefix with grams, or it could be percentages. The key thing is that these two, your initial and your final amounts, just have to be in the same unit. K, of course, is our rate constant, or in nuclear chemistry often called the decay constant. Means the same thing. Remember that this does have units that depend on the overall order. Since we're always talking about first order reactions, our K is going to have units of inverse time. So if I have an isotope that has a half-life of some number of seconds, the rate constant would be inverse seconds. If it decayed over a matter of years, the rate constant would be inverse years. So it's always inverse whatever unit of time. And then again, our definition of half-life, it's the amount of time it takes for a substance to decrease by 50%. Our half-life equation for a first-order reaction is written here. And again, remember that we're often given or we can find the half-life of an isotope. And so what's most common is to use this equation to solve for K. So remember, modifying this equation becomes 0.693 divided by our half-life. And so this is actually the more common version of that equation that we'll use. All right, I'm actually going to break this up into 2 videos. So in our next video, we're going to go through sample practice calculations using these equations.